Some of the bus driving off on the I-10 about 100 miles over this mountain range. And you go through a place called Texas Pass, which is the edge of that range.
So, all right, welcome to May's meeting. Is anybody new here? New members, or just visiting, or?
New member.
New member? What's your name?
James Edwards.
Nice, welcome. Sorry?
I'm just visiting.
Just visiting? Well, you're welcome just the same.
Right.
Just while the stragglers.
Important factors.
30 seconds.
Oh, you missed it, sorry.
We have very short.
All right, so as usual, my reports from the Sky News, which this month we are treated to in color. It's not so amazing how much a good deal on color printing. So if you want a hard copy, this will be down here in full glorious color. Actually, it's really good, so thanks. Good job. Get straight into it, Bruce.
So our current members account standing at $10,723. Our gaming account at $1,120. Happy to announce our charity tax return went in and it was okay. Because with the whole, doing that big conference here and, quadrupling or more any of the finances we usually deal with, it was kind of a big irregularity. Making that all fit nicely and writing several documents to go with it. They bought it. So everything worked out nice.
Good job, thank you. Anytime the tax man says it's okay, you can all breathe easy. Joy, anything from you, Bill?
Nothing. After minutes from last month we're in.
Are you posted on the online?
I hope so. I don't do the posting, so.
Okay, we'll figure it out. Joe, VP.
I have speakers for all the meetings except for one this year, so we're doing really well in that department. So if anyone has a speaker suggestion, please throw it my way.
Great, that's taking a load off my mind too, just having speakers. That's great. VP2.
204 members at the moment. 10 people are in the grace period, which means the membership's expired at the end of maybe March or April. So if you have any questions, please get in touch. I didn't bring a computer tonight, but you can email me or if you have any questions about your membership.
And I guess we should share the bad news that memberships are going up by
Oh, yes.
$3 for regular membership. And $3 for the family membership.
Yeah.
And $1 for youth and 50 cents for something like that. So not a very big increase, but unfortunately due to mailing costs and publishing costs and stars not aligning in clouds or something. It's not a lot for the next year for $3. So it's not a big amount, but it's Malcolm, Sanders.
Yeah, thank you. Well, to offset the price of the membership going up, the cost of color went down to publish. So,
Amazing.
by $3. So, our newsletter is in color. Other than that, if anyone wants to submit anything to the newsletter for publication, just give me an email. That'll be it. Thank you.
Good, thanks, and this is really good this week, for this month. I mean, always good, this is extra good. And just to ask me to point out that tickets for the telescope are still being sold right up until basically number 5. So you still have about 10, 15 minutes to buy tickets for that amazing telescope if you want. And then we'll have the draw. Let's get the start ready, that's pretty much organized. Public outreach, Sid.
Public outreach. The astronomy day was stupendously attended by our members. We had a very successful event at the museum. Thank for everyone who contributed. School telescope program is winding down. We got 2 more schools to go, and yesterday we attended 2 classes, one of them which we have not, but it went well. Our Galileo moment to date, as of yesterday, is 5601. And we contributed 889 volunteer hours since September 1st, 2014. And we have been out about 46 times. So we have been quite active doing public outreach program. If you'd like to help more than you have been, please let me know. I just received an email message from Senate Strawberry Festival and Senate Day. So I will be looking for volunteers. It's July 12th is the Strawberry Festival at the Beaver Lake Park, and the Senate Fair normally happens the end of August, first week of September. I don't know that your date for it.
Labor Day.
Labor Day weekend. Yes, 16th of 20, that's correct. So if you have any questions, please let me know. And I'm looking for volunteers for Be Green, which is happening on May 30th. It's a day event from 10 to 3. So if you could have solar viewing, that would be much appreciated.
Great, thank you.
Thank you.
Lori, EAO summer start parties?
Well, I'm looking around and I'm saying thank you to a whole bunch of people that I see here that are part of our summer Saturdays. We're back up on the hill, and we have got another 9. We're there for a total of 12 Saturdays this year, up from 7 last year, including International Astronomy Day. And we've had 3 so far, and they've gone very well. Our numbers have not been as great as other years, but in fact, I think we've had quality over quantity, and the people that are being here have been able to be, have had really good tours in the dome. Thank you to the people who are doing those, and in the planetary, if you don't know, we have the Center of the Universe open as well this year. Last year, we only were able to have the dome open. But this year we have the Center of the Universe open every week, and that we're up there. And so the planetary programs are on, and David Lee has been really successful in getting a set of speakers for each one of the nights that we are in there. We're not allowed to use the auditorium for 4 of the nights that we overlap in the summertime with Science Venture. But for the other nights, we've got our speakers pretty well lined up, don't we, David?
Except for next week.
Except for the 23rd. Right, so we have one for this, well, actually, it's David this week coming up. And so if you're interested in doing a beginning kind of in the night sky for one of them, and then the second presentation he's giving this weekend is on apps. On different apps and different programs that you can use for your iPads and cell phones and different kinds of things. So if you're interested in learning a little bit about what you can use and what's really good and what's not good, and what would be recommended, then that's the kind of thing we're going to be doing for that. So it's been really good that way. We are looking for volunteers, because obviously there's no way that we can expect people to come up all the time with everybody going away for the summertime. So we will be asking for more volunteers, for people who would be available to bring up their telescopes, or even if you don't have a telescope at all, just to come up and just chat to the people around. We always need somebody in the lineups For the telescopes that you are chatting to people, we need people who are on the door letting people into the dome. Like lots of different kinds of jobs we need. So if you're interested in helping out, we'd love you to just let me know. That would be just great. And I thank Diane and Joy, and Gary, they're there, who we found out how to use the planetarium projector and how to manipulate that, and we went to some training for that. And so we'll be giving some planetarium programs in there as well. So if there are any questions, I just thank you again for everybody who has been out there. Last Saturday, of course, all the clouds came in around 4 o'clock and descended on us, and so we didn't really have anything. We didn't open the dome didn't open the plastic itself, but we have lots of other things going on, so really helpful. Thank you very much.
Thanks, and I really have to reiterate the thanks that those volunteers that not only help set this up, but that show up on the Saturday nights. Like Lori said, the numbers have been great, but we're still trying to get the word out. But I kind of like to skulk off into the shadows and just listen to people talking, and the public talking as they kind of come and go between everything. Like every comment was absolutely positive, and people just rave about this. And I'm just kind of sitting there just listening to it as they walk by, and they don't kind of know I'm there. And it's just amazing. I mean, it's like Rob said, quality over quantity. I mean, we'd like to get the numbers out for sure, but people are just raving about it. So I mean, if you want to come and volunteer, it's actually a lot of fun too. It's not just like it's actually a lot of fun because the people that come to visit just super energetic, and we tend to feed off that energy too. And by the end of the night, everybody's just kind of buzzing. You don't really want to go home except we're kind of tired and everything, but I mean, it really is. It takes me like an hour to just kind of wind down to it. So if you want to come up, it's actually a heck of a lot of fun just to participate and feel that energy. And hopefully this will build throughout the summer.
And if any of you are on Facebook or any of the social media, just to take our little kind of post on Facebook, and Joe has been really good about putting something up for us, and then just getting that out, and if it went to each person in the room and sent it to another 40 or 50 people, it would start getting out a lot more. Unfortunately, the newspaper and some of the radios have not been as giving to us this year. They usually we can get something in, but they've been reticent. I don't know quite why, or I'm not talking to the right people or something. Anyway, we're going to continue to work on that, but I think social media is a place to get some of this out.
Do we have any posters left?
I have about 5, but I mean it's no problem to make more. Absolutely none. So I mean it's just a quick trip to Staples to get another little set of them made. So
And the PDF is on the website, so you can download it and print it yourself if you wish.
right, yeah, you can do that, but it is.
There's a lot of black.
It's very dark. So, but I could certainly bring some more up for Saturday, and if people have got some other places to put them up, that's wonderful. Yeah.
Okay, so let's know if you have like a lunchroom or corner store or something where you can put a poster, talk to Lori and get some more printed up.
Public library.
Library.
Yes, yeah. I think most of them are up now.
Cool. All right, thank you. Website.
I'm gonna come down there tonight. Usually I have a 1 sentence report, tonight it's 6. So. I just wanted to do a report on the migration of the website, because it's been 18 months since we moved from the old website to the new. And Matt is now providing the hosting service and did all the migration tasks. Thank you very much, sir. We're now using WordPress. I'm sure some people, if you're into the web business, know about WordPress. It certainly is an easier system to use. It has a few less features than a dedicated system in some ways, but it's a lot easier to do what it does. It does things very well. And in particular, its strong point is that it reformats based on what the browser is being used by the user, whoever's actually hitting our website. If they're using one of these, it'll reformat it to this screen. The old website was not friendly to small screens. You have to scroll back and forth, and it was pretty well commercial. So that is a really big plus with the new system. The authoring system is easy to use. It means we can get more people involved in the authoring and content of the website. We have making some progress in that regard. And we've changed our illustrious president to post her messages now, which is great. We're finding it a lot easier to administer than it used to be. So it's less hands-on. It pretty well runs itself in a lot of cases. And so we're happy with that. And another big plus is Google Search has recently changed the way they crawl the web to do those magic searches that everyone uses. And so the system we're using now is plugged into Google in a big way. So it's a lot easier to see when people do searches. That's a big deal. So I just wanted to go through that just so people know sort of the background for sort of the 18-month mark. Obviously, if you have any feedback, let me know.
Thanks, good job, you guys. And following on tech committee, Matt.
Joe asked me to follow up that report with a breakdown of this month's, for example, usage across different platforms. I can report that 54% of our visitors come from a desktop device, the other 46 on some form of mobile, either a tablet or phone. So that's very interesting. In the last month, we had 2,613 unique visitors, each visiting for an average of 1.5 minutes, navigating across about 3 pages each. So kind of targeted at whatever they're looking for in particular. I'm going to be adding in Google AdWords for the DAO evenings. I haven't had a chance to focus on that just yet, but any kind of astronomy related term, I'm going to start directing traffic toward the poster that we have. It's the best source of information, I would say. As far as VCO things, I can't remember if last month I reported about the new flooring.
You touched on it, yeah.
Okay, so there's new flooring. It looks great.
It's all done?
It's all done. Have a few extra tiles for backup in case anything happens to them. But other than that, this month, in the later half, I'll be doing installation up there with Dan's help. I've mentioned this a couple times. I just haven't had the time to get up there. But with temperatures inside the observatory reaching 28 degrees on average on a sunny day, it's something that we should do and deal with sooner. That's pretty much it. Other than that, evenings that were scheduled for this quarter, which fell on a Saturday and interfere with the DAO evenings, I sent out a notice to the mix that they could also alternatively host on the Fridays if they prefer, for not burning out. That's the report.
Yeah, okay. That 2,600 visitors, are they all local, or do you have a breakdown of where they're coming from?
Let's take a look at Geo here. Predominant bunch are from Canada, across the country. 94 visitors from the United States in that time, and a smattering from other places. Within Canada, 92% from British Columbia. So I'm going to assume also Victoria.
Okay, thanks. I don't see anybody here from light pollution committee. Any national issues, Laurie?
I haven't been here for a couple of months, and I apologize for that. But when I was away in Ottawa, I was able to go on a phone meeting that lasted 4 hours, right through the entire country. It was very interesting. It was my first one that I had done, and it was interesting to talk to a number of people and get what was happening across the country. We did a little bit of a little report on each one of our most of the different centers that were there, so we were all trying to find what everybody was doing across the country. It's really amazing is what people get up to in this organization. It was very good to be able to have Randy Atwood, who is our new executive secretary, talk to us about what's happening with the organization. Randy comes to us as an astronomer, as a very avid astronomer, and then also does this administration part of it. So it's really good that we have somebody who's got a real background in that. As we already mentioned, there has been a little bit of a budget increase for our fees, and it's mostly because two things. The budget has to be divided completely separately, so that everything that's done with like selling the handbook and all the things that are sold through the centers, that's all completely separate from any of the charity work. And so all the money that we get from selling handbooks and all that kind of thing, whereas a lot of money comes to us from that, we cannot use that in order for to put towards charity things. It's two separate budgets entirely. And so they have to really do some negotiating. And our donations at the national level were really down last year. Weren't sure quite why, but we didn't get in some of the major donations that we normally did. And so part of the whole donation and charitable status part was down this year, whereas some of the other parts were up. Anyway, what they had to do is increase our fees in order to be able to to offset some of that. Lots of things going on, and they are planning trips to the Los Angeles and kind of around area in November for people to go down and look at some of the observatories that are down in California. And then they're also planning trips into, I think Utah, is it Utah? Oh dear. For the big lunar eclipse, or for the big solar eclipse, sorry. They're also planning some things like that. So keep an eye on the website, because there's lots of stuff going on.
So do those eclipse trips include all the centers? Is all the centers getting together?
Well, they're kind of they're nationally sponsored. I mean, I guess so. I'm not sure exactly who, but somebody from the national organization is going to be getting that all organized and
partnered with a travel agency.
Yeah. So I mean, we can do our own thing, absolutely. I mean, on our end, but if you're interested in going through the national organization, they're doing a lot with that. So Halifax is coming up at the end of July 1st to July the 5th, and as far as I know, Chris is coming, and Jim, you are coming, and I will be there. Chris Gaynor, of course, will be there. I'm not sure, is there anybody else that is planning to go to Halifax? But we'll have a little bit of a representation from the end. But I think if I'm correct, and maybe Jim, you could head me off a little bit, but when we had our GA last year in Victoria, and now they're having the GA at the other end of the world in Halifax this year, that in fact we might see that some of the GAs now will be more centrally based, because they're having, there's so much travel with everything going on that they might actually find that we might be going more to the central section. I think I'm correct on that a little bit. In the next little bit, they're looking at them. So it might be a little while before they're back out here. Okay, thanks very much.
Okay, thanks, Mike. So before we get to the telescope draw, any questions or comments? Any new business?
For those people going to the GA, there's a certain percentage of your actual travel, not hotel and mini bar in the hotel or like that, but just you're actually getting their costs are redeemed by RASC. So that's something to think about. It's a small percentage, and I'll get back to you for next meeting exactly how much that is, for people thinking about that. It's a little bit back. It's not a huge amount, but there is a little bit of a kickback for people traveling from one center to another to deal with travel claims. And I need to ask them, we can send them an email to see if it's just for the rep or if it's generally. I'm pretty sure it's mostly for our reps and officials, but I don't it might be more than that, so I'm gonna check with them.
Well, just to let you know, I did it on points. I'm going on points, and it's costing me a grand total of $150 or something, rather than $12,550.
It's a pretty good deal.
So, yeah, so I'm saving the organization a little bit. So I might ask for, no, I won't do it. Orange juice, yeah. I can do orange juice in the morning.
So if there are no other questions, just remind me that, oh, Joe.
I would like to congratulate Reg and John on their article in the RASC. It's been published in the current issue for their discovery of some anomaly, I guess. What would you call it? What's the title?
It's persistent, time sequence study of a persistent meteor trend.
There you go.
I got lucky. Reg did all the work.
Congrats, haven't got that far yet, but I'll have to look at that. And just reminder to everybody, and especially our visitors and newcomers, that we meet after meeting upstairs in the astronomy lounge for coffee and cookies. So you're welcome to join us. If you have any questions, you can come up and ask us then, and just enjoy the company. So we'll turn it over to Sid to drop the telescope.
Thank you,
Unless
Sherry.
anybody wants to buy any more tickets. then
Now, we have a few more tickets if you would like to. I have been told people who buy the last one to buy, they're the luckiest one.
Don't sell any more of this.
I'll buy a ticket because I know it's like. Yeah, it's for, all the proceeds goes to our school program and also for, in public outreach expenses. All yours, fill up the whole sheet, what the heck?
John is doing it, sorry, may I just say something about the science fair?
Yeah.
Yeah, okay, because we were part of the Vancouver Regional Science Fair that was here in April, and we had some really good presentations given to us by the students. This year we were really pleased, and one of the young ladies, I think I put it in there, one of the young ladies that won one of the major prizes at the kind of the C, well, actually a junior level is what it's called. She was one of the top 5 finalists that went to, and right now in Fredericton, New Brunswick, as part of the science-wide, or the Canada-wide science fair. So she's there, and she did this phenomenal project on looking at sunsets. I think I said something, and the sunsets from the top of Mount Dove. And she did it over 13 months. She went up and she looked at where it was setting, what time it was setting, and then did all the statistical analysis on what was happening, so she could kind of figure out what was going on. It was just an amazing project, and I hope that she does really well at the Canada-wide science fair. She certainly deserves to do well on that. So I have asked her to come and give a presentation here, to give a little bit of a presentation on her project. So hopefully she'll come in probably in September or October. She'll come back and give us that.
Yeah, the science was amazing. Yeah,
It was fun.
That was my first time as a judge, and I was absolutely loving it. It was just, I'm not sure what I expected. I kind of thought it would be, overwhelming or something. I'm not sure I ever volunteered before, but I did this year, and it was just phenomenal. I just enjoyed every second of it. So when they call us up for judges next year, don't be afraid to volunteer, because it's just phenomenal talking to these kids. I mean, when I was their age, I was playing like with sticks and mud. These guys are building computers and robots. Sticks and mud.
Anyone else would like to test their luck? I think John will kill me. He's the last one to buy. He doesn't win.
I already bought it.
It's guaranteed, isn't it? With the last
That's right,
one?
Jeremy.
Something's guaranteed.
While Sid is doing that, Sherry, last Friday night, we had the last of the season openings upstairs at the U that spoke. And everybody but me there was a new member. It was quite a nice evening and worked very well. So we're very appreciative of the University of Victoria for letting us do that.
Definitely, do you have a date book for the next one in September?
Pardon me?
Do you have a date book, the date book for the next one in the fall?
Yeah, we'll do it again.
For the new members who are in districts that we get to use them very too much, and also go upstairs on about once a month. And it's just great, it's really fun to use.
Pretty exciting to use it, that's for sure.
It is, we're kind of spoiled with place here, and current technical difficulties society with these class students and this here, we have our own PCO. We get to go on Saturday night to, I mean, for anybody that's just in astronomy, this is like, so we're right here.
I put your ticket at the bottom.
I knew you would.
Anyway, you want to take it up?
What, one fell out?
That's probably mine, yeah. He took it out.
Keep an eye on me.
He's got short sleeves.
That was the Okay. Is it enough?
Let's make a. Let's make a version of the video.
I think you got it all.
I'm going to stay here. Now, who's not a member, who's just a visitor, who's unbiased? You have short sleeves.
No pressure, no pressure.
Would you mind coming here, please? The rest of the group has vested interest by picking their own. Picking their. Yeah, come in. Don't be scared. I was through. Okay, so close your eyes.
Go really deep.
John's
on the bottom.
Okay, give it to our illustrious president. Oh, no.
Actually, I think it's, sorry, reiterating, I think it's Jennifer Bigelow.
Oh, nice. That's nice.
It sure is. Oh, she will be tickled when she gets this. How about that? Well, thank you, everyone who contributed. Sorry, John. Maybe next year.
Well, if it wasn't me, I'm really glad Jennifer got it.
Okay, if there's no other questions or issues to arise, then we'll turn it over to Joe to introduce our evening speaker.
Lewis is here, great, okay. Yep, God's taking care. BJ flag, there's power over there. I'm speaking to this, like this.
Well, I have a fairly strong voice. Can people in the back hear me? No. No? You're in front row. Okay, I can use the speaker.
It's an H thing. So Lewis comes to us from the National Research Council. It's a big long trip for him.
Yeah, I do it every day.
He received his PhD in radio and space science at Chalmers University of Technology in Sweden, 1991. And has worked in radio astronomy in Europe, Canada, and Chile. And he's just spent 6 years in Alma. So, main scientific interests are spectroscopy, star formation, molecular clouds, and interstellar medium of our galaxy. And I think most of those are in the abstract for our talk tonight, so hang tight. Louis Mead.
Okay, trustee. Let's see if we can get the right screen. I think I need to do something here with the screen. Oh, look. I don't have anything with this screen. Okay.
If you don't have an account, you next probably want to shut your wireless off, because otherwise it'll keep prompting.
Okay. Let me disconnect for a second. And wireless off. I'll plug in again when I think this is good. Oh. Okay. Oh, it's in stereo.
It is. Here's your cat, so I can find it.
Oh. Is this on?
Sure. I'll let you.
Try this out here. Okay, well, thanks everybody for inviting me to speak. I was thinking back to the last time that I spoke to the RASC, and I'm embarrassed to say that the last time I spoke at a general meeting on the RASC was here in Victoria, but it was probably in 1983. When I was a graduate student here at the University of Victoria. And back in those days, I did optical astronomy. But after I finished my master's at Munich, I went on to do radio astronomy. As Joe mentioned, I did my PhD in Sweden, and then worked at observatories in Sweden and in Chile, twice in fact. And about a year ago, I came back from 6 years working at ALMA, the Atacama Large Millimeter Array, which figures very prominently in the talk that I'm going to give tonight. And so, the title of the talk is ALMA Star Formation and the SOLA project. And the SOLA is a research project, a large collaboration, which I'm involved in, which grew out of my time at ALMA. And this picture here you see is Chaplin Tor, which is a plateau in the northern part of Chile's Atacama Desert. It's about 5,000 meters above sea level. And this is the location of the ALMA Observatory. Surrounding the plane, surrounding the plane here where the telescopes are these days, and in the background, we've got all of these mountains, all of which are volcanic peaks, which stretch off towards the border with Peru and Argentina. And so what I'm going to talk about tonight is not. Well, okay. Let's see what happens. Okay. This was a clicker that I borrowed from somebody, and let's see if I can make it work. Cool, good. Okay. So what I'm going to talk about tonight is not so much the, let's say, more familiar hot universe that most people think about when they think about astronomy. I mean, the hot universe being the realm of optical astronomy, and such familiar telescopes such as the Gemini telescopes in Hawaii and Chile, the Hubble Space Telescope in Earth orbit, and then other telescopes such as the Very Large Telescope array in Chile. Now, the hot universe is really the realm of the optical instruments, the optical telescopes. The hot universe being those components of the universe which are hot enough, several thousands of degrees, hot enough to emit in the optical that we can see. And so those include, things very familiar to the RASC, I'm sure, such as, star clusters, galaxies, and the sun. All these things, of course, are very important to astronomy, but the question is, where do these things come from? Where do stars come from? How do galaxies form? How do planets form? And the answers to those kinds of questions don't come from observations in the optical realm. The reason being is that galaxy stars and planets form from the cold component of the universe, which are these vast cold clouds of gas and dust that we can see silhouetted against the bright center of the Milky Way center in this picture. And you've got all these filamentary clumps of dust and gas mixed in, which absorb the light from behind. The stars and planets form in this component of the universe, the cold component. These objects can be perhaps 10 degrees above absolute zero temperature or 100 degrees above absolute zero. They're too cold to emit radiation in the optical. So optical telescopes can't see them. And optical telescopes, as a result, can't see inside the clouds and find out how stars and planets form inside of them. There. So, as I mentioned, stars form when these large clouds of dust and gas collapse. And this process is invisible to us because it happens deep inside the cloud where the dust obscures any light from getting out. And this gas and dust are cold in any case. Of course, once the stars form, if they're massive enough, they will start to heat up the surrounding gas, and then heating and ionization will cause the gas to go into these beautiful optical nebulae that are a staple of amateur astronomy photographs. This is a photograph of the Tarantula Nebula in the Large Magellanic Cloud, which unfortunately is not visible from Victoria. One of the nice things, one of the big privileges of working in Chile in astronomy was that I had the chance to see the southern sky for the first time. And there is no comparison between the southern sky and the northern sky. And I keep pointing towards the screen. So how do we look inside of these clouds and find out what's going on inside them? Well, here's Bernard 68, which is a very dusty molecular cloud, and as you can see, it's blocking all the light coming from behind it, and stars form inside of these very dusty clouds. It doesn't matter how big an optical telescope you have, you're never going to see inside of it, right? So how do you observe these clouds, and how do you observe what's going on inside the clouds? Well, to do that, you have to observe emission which comes from the material of the clouds themselves. You have to observe the light which comes from the gas and from the dust when they are very cold. And so I'm sure most people are familiar. I hesitated about putting this slide into the top because I'm never certain whether everybody in the general public understands that radio and optical light are the same phenomenon fundamentally. So if anyone is, I know this is a room full amateur astronomers, and so, I apologize if I've insulted your intelligence with this slide. But it is important to understand the similarities and the distinctions. For instance, the optical astronomy done in the visible, that is radiation, which has a wavelength of, say, about the size of a protozoa, right? Several hundred, let's say 1,000 angstrom, 500 meters, something like that. And as sort of seen in this thermometer down here, objects which emit visible light are roughly at temperatures of several thousands of degrees, 10,000 kelvins or more. At the long wavelength end of the scale, you have infrared waves, microwaves, and radio waves. And these are very long wavelength, low energy radiation, and objects which are at very low temperatures will emit light in radio, microwave, and infrared waves. And the temperatures of these objects could be a few Kelvin or 100 Kelvin. So in the interstellar medium, you've got dust and gas particles, and they tend to have very low temperatures, and so they emit light with wavelengths in this region, in the microwave, infrared, and radio region. And so the typical wavelength of radiation from these gas molecules or dust particles would be, say, 1/10 of a millimeter to 10 millimeters in size. So very long wavelengths that you could measure with a ruler, unlike in the optical, which the wavelengths are very, very tiny. And so here's another familiar object, the Horsehead Nebula in Orion. As I mentioned before, the dust in the clouds block the light coming from behind the cloud. You can't see into the cloud in the optical. So here you have a nice silhouette of the dust cloud with the bright background of the Orion Nebula behind it. If you move into the infrared, the cloud becomes transparent because the infrared radiation can go through the cloud. And in this case, you just have a very faint outline of the Horsehead here. You can see some sort of bright edges here where you're getting a little bit of emission from hot dust at the very surface of the Horsehead Nebula. But when you're looking through sort of the bulk of the cloud through the center, it's all very, very cold. Dust and gas doesn't emit very much in the infrared. The cloud becomes transparent. When you move into the sub-millimeter wavelength, looking at the emission either from molecules or from dust, then you actually see the material that the cloud is made out of. And this is what we want to observe in order to understand what is going on inside. And so on the last panel here on the right, you can see that if you look at the sub-millimeter wavelength light that's coming from dust in the Horsehead Nebula, you can see that there is sort of a clump of dust here, and then maybe an elongated clump of dust up here, or maybe two clumps next to each other. And it's in these sort of wavelengths where you can actually probe inside the cloud and actually see what the structure of the cloud is inside. And in these sort of clumps of gas and dust is where you will find stars from it. So, yes, so the sub-millimeter light, typically we observe them using radio techniques, so radio telescopes to observe sub-millimeter radiation. And this is a very high radio frequency, say up to about 1,000 gigahertz. So it would be a wavelength of about 0.3 millimeters, and then 30 gigahertz about 10 millimeters. Now, the Earth's atmosphere is not very generous to millimeter and sub-millimeter astronomy, because the Earth's gases in the Earth's atmosphere, and especially water vapor in the Earth's atmosphere, absorb sub-millimeter light. And so it's very difficult to observe objects outside the atmosphere, which sub-millimeter waves get absorbed by the atmosphere. And that's why sub-millimeter telescopes need to be built where you have as little atmosphere and as little water vapor as possible. So sub-millimeter telescopes have to be built at high and dry sites. And the Chaplain Plain in the north of Chile is probably the best site on Earth for doing sub-millimeter astronomy. It's 5,000 meters above sea level, not much oxygen. It's in the Atacama Desert, very dry, although you can see it does get cloudy sometimes. Another thing is that it's a very large flat area where you can spread telescopes out. I mean, most places on the Earth that are above 5,000 meters are not very flat. But the Chilean altiplano is relatively flat, so it's an excellent place to put sub-millimeter telescopes. And this is another picture taken in 2004, before major construction at Alma began. The plane up there is now very different looking than what it was 6 or 7 years ago. And in a way, it's a shame, but on the other hand, it's a fantastic instrument that's been built up there. And actually looking at the objects. So, Alma, the Atacama Large Millimeter Array. It's an array of telescopes. It's not just simply one telescope. It's 66 telescopes. And this is a photograph of, well, most of the telescopes now, as they appear up at the Alma site. Why is it an array of telescopes? Why not just build one telescope? Well, there are a couple of reasons for that. By making a large number of telescopes, you increase your collecting area, and so you can see fainter objects. But the main reason is that by combining observations between the telescopes, you can increase the angular resolution that you get in your observations. So you can see finer details in the objects that you're studying in the sky. So the longer apart the baseline, the distance between telescopes, we call it, the higher the resolution. And so, again, one of the big advantages of the Chapman-Door plane is that you can spread these telescopes out over a large area, up to 10 or 15 kilometers apart, and in that way get extremely high angular resolution, so that you can really look at objects on the very, very small size scales that you could never do before. And the Atacama Large Millimeter Array is a truly international project. Arguably the first big mega science project in astronomy. And projects like this that cost $1 billion or $1.5 billion to develop are always done as a consortium between many, many countries. And so for ALMA, you have the European Southern Observatory, Europe, North America, the United States and Canada, and East Asia, Japan, and Taiwan are the major partners in the ALMA cluster. At the end of the talk, I will learn what you can clicker and the computer is set up at the screen. Okay, so I could talk about ALMA for hours. Okay, well, why not go through that? In a nutshell, ALMA is going to do a number of very wonderful things in expanding our knowledge of cosmic origins, how things form in the universe. Stretching all the way from studying the formation of galaxies billions of years ago, as well as the formation of stars in nearby galaxies, and especially in our own galaxy, as well as the formation of planets around those stars. And as everybody knows, planets is a very hot topic in modern astronomy. I think it's more than 1,000 planets, I think, are now known. ALMA is going to be showing us how these planets actually form around the stars. And as well, ALMA will say a lot about the chemistry of the clouds. You get a surprisingly complicated molecular chemistry in clouds. And the fields of astrobiology, the study of sort of organic molecules in early solar systems is fast becoming a very important topic. I can't talk about all these things today. I'm just going to talk about the solar project and star formation. And so, star formation in one slide. This is everything you need. This is everything you need to know. Okay. as I mentioned before, I mean, ALMA has exceptional sensitivity and angular resolution. And so you will be able to look at stars forming on very, very, very tiny size scales and really tease out the details of what's going on. So how does a star form? Very simple, but in principle. You have a dark cloud, a molecular cloud, and you've got a large number of these sort of dense cores inside, dense regions where the density and the mass in the cloud is higher than average. Every now and then, for reasons that are not completely clear, one or more of these cores will become gravitationally unstable. In other words, the various forms of pressure or magnetic fields that help hold the core up against its own gravity are no longer sufficient to be resolved. In which case, gravity wins, as it almost always does, and causes the core to collapse. And so inside the core, at the center of the core, you will get a formation of a very dense object that is accreting mass from above it, getting more massive and hotter, and that object eventually forms a star when it gets to a high enough temperature. But, I mean, maybe 50 years ago, these two slides were maybe all we knew about star formation. That was probably basically the scenario. Very little was understood about exactly what happens during the collapse process, during the time between when the cloud collapses and when it appears as a star. In the last 50 years, thanks to infrared and sub-millimeter astronomy, we've been able to fill in more of the steps in the formation of stars. So, for instance, a surprise. One of the first discoveries of millimeter astronomy back in the late 1970s, I guess. As the collapse happens, you get a disk around the star, which is not too unusual. But what is very surprising is that as this collapse goes on, mass is not just going into the star, mass is also going out. Protostars drive these bipolar jets of very high velocity gas from above and below the rotating disk that rotates in this way. And these, what are known as bipolar outflows, come above and below the disk plane, blowing matter away from the star. And so the formation of the star seems to be this competition between mass falling into the protostar and mass being ejected away from it in these jets. These jets are probably a magnetic phenomenon, but the details of exactly how these jets are formed is still not very clear. Helmut's going to say a lot about that. So in this competition between inflowing gas and outflowing gas, you will eventually have a situation where the outflow and the inflow have dispersed most of the gas from around the object, and it starts to become optically visible as it emerges from the cloud. And eventually all the gas is gone, you're left with a disk in which perhaps stars are forming. Eventually you end up with a main sequence star, perhaps with a planetary system surrounding it. Now, before ALMA was built, people were busy making simulations of what they thought ALMA might show when they started looking at protostellar objects at high resolution. So here on the right-hand side is sort of a computer simulation of what a dusty disk around a newly formed star might look like, and they have put in a few protoplanets which are forming in the disk of the star, and you can see also there are some rings here. These rings are areas in which, for instance, this protoplanet here is sweeping up material and sort of carving a rut through the disk along its orbit, sort of clearing away all the gas and material that's in its orbit around it due to gravitational effects. And people then try to make a simulation of what it might look like if you observed it without. That's pretty perfect. But anyway, so these are simulations. Now this is the real thing. This is an actual observation with ALMA taken during some of the first of the long baseline experiments that they did. It's a young star called H.L. Tauri. So it's a young star in the Taurus constellation. And this shows, well, it shows, it's an amazing thing. So this is the most astonishing image that ALMA has produced so far, in my opinion. You can see the disk clearly around this star, but look at the ruts. There are several ruts of various radii out in the disk. And for scale, here's what, at the same scale, this is what the outer solar system looks like. So the outermost orbit here is the orbit of Neptune. So the disk is about, say, 3 times, the diameter of the disk is probably about 3 times the diameter of Neptune's orbit. But I mean, what we are seeing here is that we are seeing the ruts which are being dug into the disk by planets which are forming inside the disk. And so almost certainly there are several planets forming around that HL. And this is an amazing feature, and almost by itself, it justifies the cost of building ALMA in my opinion. It is such an amazing result. And this was a test observation, right? So when ALMA is fully tuned up and is really performing at its best, it's going to be able to make images like this or better for hundreds of forming planetary systems close to the sun.
I can also see rays kind of coming out of the center.
Yes.
All the way around, like darkened.
Yeah.
Darkened rays. Is that something we should be interested in?
I'm not sure. I'm not certain what those are. It is possible that it is some artifact from the data collection or data processing. But I have not been able to find out from anybody exactly what those are. But yeah, I noticed it as well. As you sort of see this kind of.
They seem to be in some sort of order.
Yeah, they do. Right, but it could be some, like I said, it could be some sort of systematic problem with the data. But yeah, it's very obvious actually when you look at it. Whether it's something that's real, I don't know. So onto the SOLA project. The SOLA project, which I'm involved in, is a project of a large number of astronomers who are associated with ALMA, about 30 at the moment, to study star formation in great detail in a southern constellation. There are many star formations known in the northern sky. Taurus, Perseus, Cepheus are all famous star forming regions in the northern sky, but it's in the south where ALMA will be able to do its best work because the targets will be high in the sky most of the time. ALMA is also at a very good site, so we can make observations at very high frequencies high in the sky, which is more difficult to do when you're looking at northern objects. And so the target for our studies is the star-forming molecular clouds, which are in the Lupus constellation. And unfortunately, Lupus also is invisible from Victoria. It falls between Scorpius and Centaurus, but I mean, most of the constellation is around -30 to -50 degrees south, and so you really can't see it from Victoria. Now, here's my classical reference for the What's an ME? Well, as you probably know, professional astronomers love clever mathematics. Sometimes they're not so clever, but they work very hard to figure out new acronyms. I think we're really happy. So, where did the name SOLA come from in our project? Well, SOLA is short for Soul of Lupus with Alpha. Now, this acronym is an acronym within acronyms, and I know it wasn't my idea. But it is clever in that it represents the multinational nature of our project, because we have astronomers in North America, which is just me, and in Chile and in Japan who are in this project. And so all three languages are sort of mixed up in this thing. So sola, I'm told, means sky in Japanese. In Spanish, it means, well, several different meanings. It could mean solitary or weak, Spanish. And as I see on the cake, alma means soul in Spanish. So it's a set preferential kind of acronym. And so basically what we're doing, and please don't go at this time, but we are studying the soul of lupus through observations of alma of the sky. I'm not going to make that joke. And apologies to William Shakespeare. So, lupus molecular clouds. They are a very extensive series of clouds in the southern sky. It's about 100 square degrees, actually, of the southern sky, close to the galactic plane, close to the galactic center, where you have these clouds. And so this is a map of the dust extinction. Basically, you map of the cloud by looking at how much it extincts light from behind it. So it's kind of a shadow map of the clouds. And you can see the astronomers have sort of broken up the clouds into different complexes. Whether these complexes are physically associated or not are not always clear, but look at this one up here, 2, 3, 4, 5, 6. Lupus 2 is sometimes people call it the Klingon Warbird Nebula. Star Trek fans will notice that it does look a little bit like a Klingon Warbird, but it can also look maybe like a roadrunner. Anyway, so why do we want to observe lupus? There are other southern star forming regions. Well, first of all, as mentioned before, it's a very far south realm that hasn't been studied very much because until ALMA, there was so many telescopes within the Northern Hemisphere. It's quite close by, which means you can get good resolution, but 450 light years away, which is just as close as, say, Taurus is. Also, lupus is very rich in low mass young stars, especially the very low mass ones. For some reason, the lupus region has quite a large number of, say, the very low mass red dwarf M-type stars, which are formed in this cloud, which makes it a little bit unusual compared to many other star forming regions around. We don't understand why that is. You can see that the lupus clouds are actually up in the northern part of the lupus constellation. So that turns over there, and then Alpha Centauri is there, Beta Centauri, Southern Cross, Coalsack. Yes, sorry. Oh, Jupiter died there. Okay. Anyway, look at me started with readings of the sky. So, apart from its location and the fact that it forms a lot of low mass stars, lupus is interesting because it lives in a rough neighborhood. Here's a map now. Now we're in sort of galactic coordinates. So the galactic plane is going along here. Again, we've mapped these contours are mapped to the molecular clouds. So you've got molecular clouds that are part of the galactic disk along the bottom here. Lupus is up here in these clouds. Actually, the Ophiuchus clouds are over there. But lupus is squeezed between two OB associations. The upper Scorpius OB association, which is here. And so these stars are the OB stars in that association. And then towards the west, you've got the more extended upper Centaurus lupus OB association. And so these OB associations, of course, are composed of very massive hot stars, which produce a lot of ultraviolet radiation. They produce very strong stellar winds. And they also tend to go supernova from time to time. And so the region in which lupus is living is quite different than, say, a region like Taurus, which is a very quiescent, quiet region. The evolution of the cloud and the formation of stars in Taurus can go along, it can sort of putter along with a disturbance from the outside. But in the case of lupus, the clouds have probably been affected by this ionizing radiation from the ultraviolet has been pushed around by wind and supernova explosions. And the interesting question here is that, has that different evolution mean that star formation in Lupus is somehow different from the star formation in, say, Perseus and Taurus? So, I'd like to tell you that I've got lots of ALMA results about the Lupus reading to show you today, but I don't. Getting time on ALMA is hard. Since it's the premier sub-millimeter telescope in the world, it is very heavily oversubscribed. So only about 10% of the observing proposals that are accepted by astronomers to use ALMA are successful. And a lot of research has already come out of that. About 200 papers have been published since 2012, and that was before the telescope was even finished. They started observing when a subset of all the antennas were available. So, given the difficulty of getting time on ALMA, it's very critical to prepare your project very carefully. And so, you need to know what your targets are, you need a strong cyber space, you need to have done your homework before you go off and try to ask for ALMA. So what we've done for Lupus, we spent the last 2 or 3 years surveying the literature to find out all that is known about star formation in Lupus. And we've also made some observations ourselves with other telescopes to help buttress our case for getting ALMA observing time. And so, for instance, we have used the Herschel Space Telescope, which is a far-infrared sub-millimeter telescope outside the Earth's atmosphere. We collected data from their archive, basically again showing where the clouds are, the dust emission. And we've been looking also, identifying all of the different objects which are in the region. This is Lupus 3. So for instance, the green dots are areas that we think are pre-stellar, areas where dust cores where stars may form in the future. The red ones are actual protostars. Only a few know that we know about at the moment. And the purple and blue are sort of older stars which are coming out of the cloud, dispersing the gas around them, but maybe forming planets. And so it's very important. You will never get ALMA time to observe this huge chunk of the sky. You have to concentrate on the objects that you need to target very carefully when you're going to observe. So to get time. One fun thing, we were able to do some mapping of Lupus using a small telescope, which is also on the Shackleton Plateau. There are small telescopes scattered all over that area. If you wander around, you're going to walk into one. And this one is about 8 kilometers, I think 8 kilometers northeast of the center of the ALMA array. It's a Japanese telescope, a 10-meter dish called the Atacama Sub-millimeter Telescope Experiment. And it had a, say, millimeter wave camera. It only has 144 pixels, but still, it's okay. To take images of the dust emission from these cores and mosaic them into a large image. And it was a lot of fun observing at ASC. Here's the control room right here. And now it doesn't matter that you're at 5,000 meters on the driest desert on Earth. The Japanese are going to stick to protocol. So when you walk into the control room, you have to take off your shoes and put on these little sort of comfortable little booties before you're allowed to walk into the rest of the building. I thought that was incredibly charming. And also a very good tea there as well. So that was a lot of fun. So we observed Lupus 1 region using this telescope and the Aztec camera. It was called the Aztec camera. Now this is another one of those acronyms. But you know what? I don't know what that acronym means, and I have not been able to find out. I've looked at every paper published about Aztec, including the paper that describes the instrument by the engineers who built it, and they do not say what it means. Maybe the TEC might mean thermal emission camera, possibly. What AG stands for, I don't know. The only hint perhaps is that this instrument was designed to be installed on a radio telescope which is being built in Mexico. So that's the only thing I can think of. I think they were stretching a bit farther for that. Anyway, here's our map of Lupus 1 that we did with the Aztec camera, and you can see, sort of the long filamentary structure of the clouds, but you also see these sort of very we think that stars will form. So these objects, in various places across the cloud, are the targets of our observations. So this year, after perhaps 3 years of preparation, we decided to take the plunge. The fourth round of our proposals, the deadline for that passed several weeks ago. 1,582 observing proposals. Wow. Which is a new record. Every year is more. And well, our consortium, we only submitted 5, but I mean, it was a lot of work submitting those 5 proposals. And in the last few slides that I have, I'm just going to very briefly go through just some of the main science themes of those 5 proposals, just 1 slide each. I won't go into the details. You can talk to me about that after coffee. So, one project is looking for the protostellar jet in Iris 15398, which is a protostar in the Lupus region, which is driving molecular outflow. As I said before, protostars drive outflows that sweep up gas. And in this case here, you can see this emission from molecules. You can see the disk here. This area here is the disk. And you can see the walls of the cylindrical cavity of the outflow. And inside the cavity is where the wind or jet that drives the outflow is coming from. And we know very little about it. We don't know what causes it. We don't know how it's driven from the star. But we do think that it's probably atomic or ion, it's not molecular. And so what we're going to do here for this proposal, which is proposal number 136, if you haven't been on the time allocation committee, is to observe with our at 809 gigahertz in these 3 fields here, circles, around this object. So it's here, the jet should be along here. To observe the 809 gigahertz spectral line of atomic carbon, which is a very good line for observing atomic gas at these frequencies. And we'll be testing the experiment. Hopefully we'll get time. Hopefully get time for this one as well. We also want to map the magnetic fields around protostars in the Lupus area. And so here's a map again of Lupus 1. The little red and green lines here, which are mapping out the direction of the magnetic field in the cloud. And that's measured by looking at the polarization of the dust emission. And you can see that the magnetic fields seem to be mostly perpendicular to the filament. And the idea perhaps is that the filament is sort of collapsed along the field lines where there's less resistance. And the implication being that the magnetic field is important for understanding how stars form inside the cloud, because magnetic fields are a form of support. It will resist gravitational collapse. But the question is when protostars start to form in these clouds, will the magnetic fields stay aligned with the fields outside, or will they decouple themselves? It's quite important to understand that, particularly since the outflows seem to be connected to magnetism as well. And you expect the outflows to be along the magnetic field lines. The question is what happens to the magnetic field lines when you get very close to the protostar? And with ALMA's resolution, we should be able to say something about that. Another proposal is to search for disks around binary stars. Of course, most stars are binary, not single stars. And so what happens during the star formation process when there are 2 stars involved and 2 disks are involved can be very different from sort of the cartoon picture that I showed you before. We don't have the answers to many basic questions. For instance, do disks form around both stars in a protostellar binary? Does the massive star have the most massive disk? Always. Or do the disks interact in some way? We don't know. We have very little information about that. This is actually another ALMA observation. This of the binary star HK Tauri, not HL Tauri, but HK Tauri. ALMA seems to be going through the alphabet in a very systematic way. And here you can see the colors indicate the direction of motion of the disk velocity, either towards you, with the blue shifted emission, or away from you, with the red shifted emission. So showing you how the disk is rotating in this binary. And surprisingly, in this binary, you can see that the rotation axis of this disk is probably along this direction. Probably close to the plane of the sky, because the disk is quite edge on. The other binary has a disk, but it's not as edge on, and it looks like the axis is maybe more along this direction. So it seems that the rotation axes in these binaries may not be aligned. And that will have, why is that? Are the disks interacting with each other? What does that do to the formation of planets in these disks if the disks are being talked about? It's very important to understand what happens in binary star disks, because that will affect how often you'll have planets in binary stars. And binary stars are the majority of stars. And so in our proposal, 197, we've made a list of all known young binary stars in the distribution, and we'll be asking to make observations of all of them in order to map out the disk and how the disk is rotating. In order to get statistics about how often the disks are aligned, how often they're not. And next to last slide, this was a pet project of one of our Japanese colleagues. He wanted to observe a young variable star called EX Movie, which happens to be the prototype of the EXOR class of eruptive variables. Basically, these are very young stars with a disk, which are still accreting material from the envelope. And from time to time, enough material falls from the envelope onto the disk that the disk will become unstable and then dump mass onto the star, which we'll call an optical flare-up in the star. And these guys are variable on timescales of months to years. And so here, this object actually had an outburst back in 2008. Here's the visual magnitude. Back in September, October, you can see it was around 12.5 magnitude. And then there's no data here, but sometime between October and February 2008, the star had an outburst, jumped up to around magnitude 9 or so, and varied irregularly, and then dropped back down again. And so during the time when it was in its high state, it was probably dumping material from the disk onto the star, causing an outburst. And we know very little about this, what actually happens with these disks as accretion goes through. And again, it affects the structure of the disk and what happens to the disk. And in this proposal, we hope to, again, just observe the disk around EX would be to understand, how big is the disk? Is it very massive? Is it likely to be unstable? How is it connected to these outbursts? And here there's we have some simulated observations about what we think we might see. Basically, each of these images shows gas at a different velocity. And so you can see the rotation of the disk by looking at the change in the pattern of the emission as you look at different radial velocities. And hopefully, our model prediction will be matched by the observations we get. But hopefully, maybe not, because the unexpected is actually more interesting than the expected. Confirming models is not so much fun, that's why they're wrong. Finally, last slide. Always last slide. Last proposal. Young brown dwarfs. Brown dwarfs are very, very low mass objects, less than a tenth of a solar mass, which are on the boundary between stars and planets. They're not massive enough to burn hydrogen in the nucleus. And so they never become stars. We think there are a lot of brown dwarfs, they're hard to see. But there are many questions about brown dwarfs. We don't know how they form. There are basically two different ways a brown dwarf might form. The first model has a cloud core, which collapses to form a disk and a protostar. And then in the disk, at some point, this brown dwarf forms and then either gets ejected from the system, or the disk just sort of disappears around it and it flies off as a separate object. And in this case, if it's ejected from the system, it's unlikely to have its own disk and its own envelope. And so you would expect brown dwarfs to just be single objects. The other possibility is that brown dwarfs form like stars, but just in smaller clumps. So smaller cores which collapse, again, could form a disk. And these brown dwarfs then in that case might actually have disks. Brown dwarfs might actually have different. So at the moment we don't really have any idea which of these two scenarios are right. Maybe both are, depending on the circumstances. But as I mentioned before, Lupus has a large number of very low mass stars, and so it probably has a large number of brown dwarfs. And so we have a list of brown dwarf candidates, and we want to observe these candidates with ALMA in order to see whether they have disks around them. And we'll be able to say something about how these disks form, how brown dwarfs form. Now, I've probably gone on too long. I apologize for that, but I'd like to thank you for your patience. And, you know, the punchline, the final slide is that, you know, the goal of our consortium is to make Lupus as important a region for understanding of mass star formation as any of the more famous traditional classical objects in the northern sky. And, you know, hopefully with ALMA, we've got, you know, the ultimate truth in order to do that. And so, thank you very much, and I'll take some questions.
Are there any questions for this? Yes.
Earlier in the talk, you talked about tuning ALMA. What do you mean by that? What would you check?
Okay, I meant tuning ALMA in sort of the, I guess, the most general case. I mean, at present, not all of the observing modes of ALMA have been commissioned and verified. There's still probably work to be done, including the calibration of ALMA. As you can imagine, the facility is so powerful that the pressure to observe with it from astronomers was so great that it was pushed into service as early as it possibly could be. And so, I mean, it has not been, let's say, fine-tuned to its best performance yet. Right? I mean, ALMA will improve even, you know, these images are just a taste of the wild when it's fully up and tuned to be the race car that it is, it's going to produce some amazing results.
I was wondering, when you're doing an observation of an object, how long are your exposures on?
Okay, that varies a lot. ALMA is an interferometer. ALMA is not a camera in the sense of optical astronomy. What you have is that you have a resolution element on your object. And then because of interferometry, you can actually sub-resolve that beam and make an image. The image will be limited by the beam size, basically the point spread function of the telescope, which for radio telescope is much larger than for optical telescope. It depends upon the sensitivity. I mean, for a lot of the observations that we're planning to do in our project, we estimate that tens of minutes can often be enough to reach your science goals. I mean, ALMA has so much collecting area that it can do in a few seconds an observation with the sensitivity that it would take an older, smaller array hours to do. I mean, it's basically 10 to 100 times faster, more sensitive than the previous linear telescope. So these are like our 5 observing proposals sound like a lot of observing proposals, but it's not a very large amount of observing time. At the moment, I think people are getting a couple of hours of observing time typically in the project. I think think 24 hours of observing time would be considered to be a large project at this time. It would be very difficult to get 24 hours of observing time. But that 24 hours would probably be spread over multiple objects.
With 60 or more desks there, can they all work in concert, or could you actually observe multiple objects at once?
That's a good question, yeah. You actually can split the array up into subarrays. And then each subarray then can observe a different object independently. So, I mean, our data collecting system is able to accept multiple streams of data from different observations simultaneously. Of course, you pay a price because you will get less sensitivity in each observation because you're using fewer antennas. But at the moment, I think that we can make, 3 subarrays, and I think in the future, maybe 4 or 5 subarrays may be possible. How often that will be used is not clear, but it was technically not difficult to do, and so it was included as part of the observing system. But it's not like an option, you can't take your optical telescope and do that.
I'm trying to understand a little bit more about what these brown dwarfs could be or might be. If a planet like Jupiter were somehow ejected from the solar system and went off on its own, would it be considered a brown dwarf?
The boundary between, now we're getting into is Pluto a planet? I don't want to talk about that.
I didn't ask about Pluto.
No, it's a similar thing. I mean, what's the boundary between, say, a brown dwarf and a gas giant? Right? In many respects, they are very similar. The boundary between a brown dwarf and a star is a little more clearly defined because you say basically a star can burn hydrogen in its core, right, and a brown dwarf can't.
Yeah.
Right. Although in its early stages, the brown dwarf may actually burn lithium or deuterium for a short time. So brown dwarfs tend to be much more massive than, say, Jupiter. They're 75 or 100 times more massive than Jupiter. But they're not much larger in size, actually. They are very similar in size, they're just much more dense. In terms of understanding what you call a brown dwarf, perhaps the best way to do it would be just look at its spectrum and use a classification system similar to the normal stellar classification system, in which for a brown dwarf, if you see strong bands of methane and other CH4 and other molecules, you may just arbitrarily decide this is what a brown dwarf is. A brown dwarf has these particular kinds of spectral lines. But the boundary between the two is rather fuzzy.
Some of those lines would come from the Jupiter thing.
Yeah, exactly.
One last question.
Would there be some places where you are looking at, say, the Lucas areas and you want to do some work there, but there might be somebody over in Japan that actually wants to look at the same region but is doing something like something that they would use the same part of the sky to look at, and that they could use, that you both could use the same data so that you could kind of put your proposals together? Like to get time to take that picture?
Yes.
Or that big, or that, or very specific.
Well, a decision was made early in the project that there would be a single time allocation committee for the whole world. And so all the proposals go in one big bucket. And of course, different regions get observing time based upon their contribution to the program in proportion. But the proposals are ranked in order of scientific merit as a whole. And I think the ALMA board, and probably Jim can talk about this more than I can, agonize us a lot over the rules for what do you do when you get a duplicate observing proposal, or an observing proposal which is very, like you say, looking at the same area, maybe even the same kind of observation, but for a somewhat different science goal. And in the very early stages of ALMA, I think there were some cases where proposals were, say, strongly encouraged to collaborate together instead of
Trying to compete with each other.
in some cases, these groups did compete. I mean, there are some examples where two research groups that, shall we say, were friendly rivals, had made proposals to basically do the same science with maybe the same objects. And in those cases, I think that basically one set of observations would be done. The data would be sent to both groups at the same time, hopefully, and then they would be off to the races. And whoever publishes first, publishes first. So yes, especially since ALMA can, at the moment, ALMA is skimming the cream off. It's such a powerful instrument that it can point it at almost any object and make it discover. It's that good. And so there are all the projects which are being done at the moment are the obvious ones. And and so that means that everybody is asking for the obvious ones. And so I don't envy the time allocation committee. It's probably sorting through 1,400 proposals, trying to sort out region and science and group. No thanks.
But Louis, there's another aspect to that question, I think, which is all modern observatories now have data archives.
Yes.
And so people are already going into the ALMA archive, which is only a couple years old, and doing research that wasn't done by the PIs. And I think that's just, it's something which is just, it's amazing how the concept of archival research has really developed, first from Hubble, which was a lot easier to do than ground-based telescopes, but now very, very common with ground-based telescopes.
You get it, say, for
So if they get time, they'll have a proprietary period of a year, or is it 18 months? I can't remember.
Yeah, I think maybe 18. I hope it was 18 months.
Yeah, but after that, it's open to the world.
The data goes into the archive and it's available to anyone. But of course, we have a head start. But Jim is right about archival research becoming very important. And with ALMA, it's a fire hose of data that we're getting. And it's very for observations where you have a large number of spectral lines involved, one group probably doesn't utilize all the data to achieve their science goals. And there's probably gems of information just sitting in the archive waiting for a clever person to come along and pull them out. So, but it's better to do it first. I mean, you can sit around, you can sit around and say, well, I'll just wait for the archive data. But you don't it's hard to stay at the forefront of that.
Louis, thank you very much for your candid answers. I know you're a bit nervous talking about a project that's still not completely flying, so, but I'm glad you did. It gave us a good insight into how ALMA works and what you're looking for in your project. Thank you very much.